This is my second session on gyroscopic couple. In my previous session, we have primarily seen two important things: that what is a gyroscopic couple and why there is a gyroscopic couple. In this session, we are going to mainly focus the application of the gyroscopic effect, or we can say that where in the engineering application we observed a gyroscopic effect. We will also try to solve some of the basic problems. So I will start with the gyroscopic effect in particularly rotors. Then we will move on the gyroscopic effect for flying aeroplane, and then we will see it in the automobiles. Particularly we will focus for the four-wheeler, and then we will see for the two-wheelers. So I'll just give you in brief 2-3 things. First is that what we have already seen, that if something is rotating with certain angular velocity, and if I will turn this axis with some angular velocity omega p, I observed a particular effect with respect to the third axis, and that particular effect or torque is known as the gyroscopic effect. I call this axis of spin, where I am having the rotating axis. Then we have the axis of precession. This is particularly axis about which we turn the complete rotating axis, and because we turn the axis, suppose we turn the axis with an angle del theta, we observed a gyroscopic couple in about this axis. Second important thing that we have to understand before we go in the detail of this is that if we are having something rotating and we want to represent this omega of this rotor in vector form, that basically follows with the right hand rule or the screw rule. Suppose in my case this is rotating and I am observing from this side, because it is also important that from which side you are viewing the component. Suppose I am looking from this side, and from this side I am looking that it is rotating in the counterclockwise direction. So if I am having a screw, and that screw is, this is my screw and this is the screw, and if I am rotating something in the counterclockwise direction, that means the screw is coming in this direction. So when I will make the vector of this omega, the direction of the vector will be towards the left. On the other hand, if I am having a rotor and the rotor is rotating clockwise direction, I am looking the rotor from this direction and it is rotating in the clockwise. So if I am having a screw and the screw is also rotating in the clockwise direction, when I will rotate the screw in the clockwise direction, the screw will go in the forward direction. That means if I want to make the vector omega, the direction of the vector omega will be towards the left side. So with that note, I will start the today's session. Initially I am explaining the phenomena for a rotor, and this picture is showing that there is a rotor. We are having a rotor which is aligning along the x-axis. This is my x-axis, this is my y-axis, and this is my z-axis. And if I give a rotation to my rotor with certain value del theta, the rotor will finally reach to this position. This is the position 1 and this is the position 2 of my rotor. And because of this rotation, one of the component of angular momentum will change in this YZ plane and another component will change in this XZ plane. I am showing here two reference planes. So because of the change in the angular momentum on this plane, we received a reacting torque or a reacting couple in this direction, and because of this we receive a gyroscopic effect along the y-axis. What we are doing, we are having an axis of spin along the x. This is my spin axis. I am giving a precision about my z-axis, so this is my axis of precision. And when it will reach here, the change in the angular momentum, suppose this is my reference plane, one reference plane which is YZ plane and another reference plane is the XZ plane. When the rotor will come here, one of the angular velocity component will be here and one of the component will be here. All these things we have seen in detail, we have checked in detail in my previous lecture. Here I am just giving a recap that if I will rotate the rotor I will be having a gyroscopic effect because of the change in the angular momentum of this plane, and because of this plane I am having an effect about the y-axis that will basically give an upward or downward movement to my rotor. Another way of presentation of this three-dimensional system is that by using the two-dimensional plane. Suppose I am giving a top view to my system, and this is my top view. So when I will see it from the top, I will be able to see the XY plane. So suppose this is my XY top plane. This is my x-axis. Suppose this is my x-axis and this is my y-axis. So my angular velocity, initially it is along the x-axis, and now if I will give a rotation to del theta, my angular velocity vector will be here. So this is my active torque. When I am moving my rotor from here to here, or I am giving certain active torque or precision torque, so this is my active value. Because of this active value, I received a reactive torque, and which gives rotation to the axis of this rotor, maybe in upward and downward direction. Suppose in this case, this is my active torque, which is going in this direction. If I will represent this line in this plane, I will see that it is going in this direction, and because it is going in this direction, the reacting will be in the opposite direction. So this is my active torque and this is my reactive torque, and reactive torque is coming in this direction and something is coming in this direction. And if follow the screw rule, I will see that if something is coming, that means that it is, if I am watching from this direction, something is moving in the counterclockwise direction, and because of that I will be having a counterclockwise movement, which is gyroscopic movement. And because of the gyroscopic movement, this rotor axis will try to move in the upward direction. Upward direction means this will be try to move in the ZX plane in the positive Z direction. So this here I am representing, suppose this is my x-axis and this is my z-axis. So initially rotor was here, and when I will be having a gyroscopic couple in the counterclockwise direction, it will try to lift the rotor and rotor will go in upward direction. So I will give a brief review. I am having a rotor about this axis, and my axis of rotation is called the spin axis. I am giving a precision about the z axis, so the rotor will move in the horizontal plane with an angle theta. As the rotor is going here, there will be change in the angular momentum of this plane and this plane, and because of the change in the angular momentum of this plane, I will be receiving a reactive torque, and that reactive torque giving an anti-clockwise movement to the rotor. And when I will be having an anti-clockwise movement to the rotor will lift. This can be shown by this picture, that initially the rotor is like that and it is lifting because of the angular couple coming up due to gyroscopic effect. So now let's see one numerical problem which is stating that I am having a rotor, and the rotor is rotating and the mass of the rotor is 10 kg and the radius of gyration is 120 mm. It is having a cantilevered kind of arrangement, but this is not exactly cantilevered, because when we have a cantilever, this end is fixed to the cantilever, but here the end is A is free to rotate. That means we are having a universal kind of joint here, so that it can go in upward, downward direction as well as in horizontal, front, back, upward, down. Every kind of joint is possible in joint A. And then we are saying that the rotor is rotating with an RPM, that value is 200 RPM. When see from point P, if I am looking from here, I am saying that the disc is rotating in the clockwise direction. So when I will look from this direction, it is rotating in the clockwise direction, and suppose I want to make the angular velocity vector of that, so I will see that from this direction I am looking at a screw which is rotating in the clockwise direction. So if the screw is rotating in the clockwise direction, then definitely screw will go in this way. So my angular velocity component will be shown by this line. This is basically my omega. Now it is saying that this complete body is just free to fall down, and what he is saying that if I will give a precision about this axis, because of my precision there will be a net gyroscopic torque about y axis, and which will lift the rotor. so that the rotor will not fall down because of the gravity. So I'll read the statement that there is a disc of mass 10 kg and the radius of gyration 120, and it is having a cantilever time arrangement, and it can fall because of the gravity, but it is rotating within a clockwise direction with 200 rpm, and I want to give a rotation to this rotor about z-axis. That means we want to give a precision angular velocity to the rotor so that it remains in the horizontal position. So now let's see the solution of our problem. Suppose the rotor is rotating in the, if I am looking from this direction and the rotor is rotating in the counterclockwise direction. I want to correct the question that this, if this is not clockwise, if it will be clockwise, it will be like that, but if it will be counterclockwise, the direction of the rotation will be towards this side. If I will see from this side, because if it is rotating in the counterclockwise direction, the screw will comes out. Suppose this is my screw this way, I am looking from this side and it is coming out, it is rotating in the counterclockwise direction, so the screw movement will be in this way. So this will be my omega. So now this is my rotor. I am assuming three axes. One is the x-axis, this is z-axis, and this is y-axis. If the rotor will be stationary, it will fall because of the gravity, and the rotor will just like in this position, because it will rotate and it will come in this way, but it cannot go anywhere from this point A because it's a universal joint, but it can rotate about this point. So basically what is happening, that there will be a gyroscopic couple with respect to the y-axis, which will give an upward motion to my rotor, and that upward motion will be balanced by the gravitational force, and therefore my rotor will remain in the horizontal position. So now let's see that what we need. We need to rotate the rotor, and second thing, we have to check whether we want to rotate in the clockwise sense or in the anti-clockwise sense while we are watching the rotor from the top view. So I will consider both the cases. In one case, this is my first case where I am saying that I am giving a rotation in this way. So my rotor, or this is my angular velocity vector, which is initially in the along the x-axis, and if I will give a rotation to my vector which will go in the other direction, if this is my minus y direction, the rotor is going in the minus y direction because of this precision rotation. And if it will go in this way, what would be the sense of the gyroscopic couple? So let's assume, let's see the top view of this. From the top view we can see this is the initial omega vector and this is the final omega vector. This is my active torque which try to rotate the this rotor in the xy plane and towards the minus y direction. So if I'll see, this is my x-axis, this is my y-axis, but basically this is my minus y and this is my plus y, if I am following the same convention which are here and here. So this is my active torque which is going inside the plane, and this is my reactive torque which is coming from the plane. If I will go back to the 3 dimension, I will see that the inside the plane is the active torque and coming out from the plane is the reactive torque. And if something is coming out from the plane, that means my screw is rotating in the counterclockwise direction, and if it is rotating in the counterclockwise direction, then I will be having a gyroscopic movement which will be in the counterclockwise direction. I know that the couple value is defined by the angular mass moment of inertia of the rotor, then the rotation of the rotor and the precision omega of the rotor. So this is my precision angular velocity, if omega is my rotational velocity, and if I is the mass moment of inertia which is given in this question and defined by basically mk square. Both the values are given to us. So I will be having a torque which will be in the counterclockwise direction. That means this axis or this rotor will go in the upward direction because of this, because if I am having any couple which is counterclockwise direction about y, which it will try to move the whole system in the upward direction, and this is the case which I am looking for, because if the rotor will go in the upward direction, it will definitely balance the load which is going in the downward direction because of the gravity. Even though I am showing the second case, that if I am having my rotor, this is my rotor, and if I am giving a precision in the opposite direction, so my rotor will comes out in the positive y direction. So it is coming out in this way. So this is my active and this is my reactive. Again I am showing it in the two-dimensional plane. This is my x, this is my minus y, and this is my plus y. So now the rotor axis is coming to the positive y direction. So this is my active and this is my reactive. If I'll go back and see in the three-dimensional, my reactive is going inside the plane, and if something is going inside the plane, that means the couple about the y will be in the clockwise direction, which will basically try to again move the rotor in the downward direction. So if I am having this case, my gravitational force as well as my force due to the gyroscopic effect will both in the same direction. So now I have understood that if I want to keep the rotor in the horizontal position, case 1 will be the right case for me, because in case of in the second case, gravitational force as the gyroscopic couple effect both are trying to pull the rotor in the downward direction. So now if I want to calculate the exact value, I have the formula that my I can calculate using the mk square. My mass is 10 kilogram and this radius of gyration is 120. So this is my mass moment of inertia. My angular velocity is given in the rpm, so I can convert it into radian per second. And if I will balance the two couple, I want to balance the couple, because this is my rotor and the rotor gravitational force is trying to move the rotor in this sense, and this is L. So the couple which is because of the gravitational force will be mgl, and that mgl is basically going to be balance of my gyroscopic couple, which is in the counterclockwise direction and defined by I omega p. When I will balance these two, I am having that my precision rotation will be 6.5 radian per second. See the gyroscopic effect in the aeroplane. So for that I am showing a picture of an aeroplane. Suppose this is an aeroplane and the aeroplane is going in the positive x direction. When I am looking from the back side of the aeroplane, I am looking that the rotor of the aeroplane is rotating in the clockwise sense. So this is my plane going in the positive x direction. I have considered that this is the y direction, this is x direction, and this is my z direction. And as I said that from the back I am looking that the rotor is rotating in the clockwise sense. That means if I want to make the velocity angular velocity vector, I have to first check the screw rule, and based on the screw rule, if something is rotating in the clockwise direction, if I am looking from this side, the screw will move in the forward direction, and therefore my velocity vector will be defined by this arrow. So if I want to analyze the gyroscopic effect in the plane, basically what happens when the plane moves and it is having a rotor which can be considered as an equivalent rotor which is rotating, and suppose someone wants to give a turn to the plane. Suppose this is my plane and I want to turn the plane in the left direction. So when I want to turn my plane in the left direction, basically what I am doing, this is my rotor and I am giving a precision to my system about the vertical axis. So this will be the precision velocity, this is my angular velocity. So definitely I will be having a gyroscopic effect about the y-axis, which may lift or pull the nose of the plane in the plane, means the nose of the plane may go up or may in the down. So let's try to analyze this effect properly. So I have made here a plane which is basically the plane of flying of the my aeroplane. This is my x-axis, sorry, this is my y-axis, this is my x-axis, and this is my z-axis. And suppose this is my angular velocity vector, which I have already shown here. So this is my omega vector, and suppose I am taking a left turn. So when I will take a left turn, basically I am giving a precision to my plane about the z-axis, and my angular velocity vector will now be drawn in this way. So this is my initial position, this is my final position, and this is a three-dimensional figure. If I'll go back and I'll make a two-dimensional figure, so from the top view I can say that this is my angular velocity which is along my x direction, and this is my negative y, and this is my positive y. Then I am giving a left turn, that means my angular velocity vector will come here. So this is my new position of angular velocity, and this is my del theta. So basically this is my active torque, and if this is my active torque, the reactive torque will be in this way. And if I will go back to the three-dimensional space, I will be knowing that this is my active direction and this is my reactive direction. So basically the reactive direction is a thing which is coming out in this way. So if something is coming out in this way, that means if I will apply a screw rule here, the screw rule will say that screw is coming in this direction, and the rotation of the screw is in the counterclockwise direction. So I will be having a couple, that is because of the gyroscopic effect, and because of the gyroscopic effect there will be a counterclockwise couple will act on the plane. So if this is my y-axis, I am having a counterclockwise couple about the whole system. So because of the counterclockwise couple, the nose will go in the upside and the tail will come in the downside. So if I will see from this way, so this upward will be my z-axis and this will be my y-axis and this is my x-axis. So I will see my x and z-axis, this is my plane which is going in the forward direction. This is the same representation, and because of the gyroscopic effect which is coming about in the counterclockwise direction, the whole plane, this part will go up and this part will go down. So normally there are two types of problem we solved in the case of aeroplane. One is that if you are going in the sky and suddenly you want to turn your plane in the right side or left side, so based on the rotation of the rotor, the plane nose will go up or down. On the other hand, if you are moving on the space and suppose you want to land, so what you will do, you will go downward in this way, means you are intentionally giving a precision about y-axis, and when you are giving a precision about y-axis, you will be having a gyroscopic effect about the z-axis. So when a plane is moving in the space and suddenly if he want to land to the ground, its nose will go in the downward direction, and because of the gyroscopic effect, the plane will either turn toward the left or the right based on the direction of the front rotor. So now I am taking the second case where I am saying that if the plane will take a right turn. In this case the plane was taking a left turn, so when the plane was taking the left turn, my gyroscopic couple was coming out counterclockwise about the y-axis. And now if I will say that plane is taking a right turn, so when the plane will take the right turn in this picture, the initial condition of my angular velocity here and the second position of angular velocity will somewhere here. So this will be my active, so this will be my reactive. So this is my reactive and this is my active. Active means we are applying to our system or we are giving through this precision axis. So I am giving a right turn to my plane. Suppose this is the second figure and this is the direction of the motion of the plane, and I am giving a precision to my plane about my z-axis, and because of this precision the plane will come here. Please understand, in all these cases this theta or the change in the direction of this rotor angular velocity is very small, and as we just give a rotation, suddenly the gyroscopic effect comes into the picture and it gives an opposite force or a different force to our system. So if I am having my angular velocity vector in the forward direction and this is my tilted angular velocity vector, this is my active, this is my reactive. So basically my reactive will go inside the plane, and something is going inside the plane, that means what? The couple will be in the clockwise direction. So in case of my aeroplane, when I will be having a plane moving in this direction and this is my top vertical Z direction, this is suppose my Y direction, and this is suppose my X direction. If I am giving a precision to this way, the plane nose will go down and tail will go up, which is equal in opposite to my previous case. So I can see here, if the plane is going in this direction, I am viewing from the back, it is rotating in the clockwise sense, so my angular velocity vector will be drawn in this way. If I am giving a left turn, the angular velocity vector will basically go in the minus Y side, and this is my active direction, so this is my reactive direction. Reactive means something is coming out towards the Y, positive Y. That means the torque will be, because if something is coming towards positive Y, and if I am having a screw here and this is my screw suppose, and screw is coming in this way, that means we are rotating the screw in the counterclockwise direction. So I am applying a counterclockwise couple to the plane, and because of that the nose will go in the up. On the other hand, if the plane is taking a right turn, the nose will go in the downside. So now let's solve one problem. Here I am having a problem that there is a plane in the space which is flying with a velocity of 240 meter per second and taking a left turn with a circle of radius 60 meter. That means what? That I am moving a plane. Suppose that if I am looking the plane from the top view, suppose this is my plane, this is the rotor of the plane, and this is my plane. The plane is going in this way, and plane is suddenly taking a left turn, and the radius of the turn is defined by the 60 meter. So what this 60 will be useful, and how this 240 will be useful, we will see later on. So now let's complete this statement that if I am having it is rotating with a radius of 60 meter, the mass of the engine is 450 kilogram, and the radius of gyration is 320 mm. The engine speed is 2000 rpm when viewed from the rear. That means this is my plane. I am looking from the back, and it is rotating in the engine speed is 2000 rpm when viewed from the back, but in this question the direction is properly the clockwise. So it is rotating in the clockwise sense when I look from the back. That means the angular velocity vector will be in this direction, because my screw will go in the forward direction. So now suppose my plane is moving in this way, and I want to turn the plane towards the left. It means if this is my forward direction, this will be my left direction, this will be my right. So plane will try to turn in this way. So this is my angular velocity vector initially. This is top view. This is 2D plane. Basically here I am having two axes. One is the X and another one is the negative Y, and this is my positive Y. If I will compare these two figures, so I am moving my plane towards the negative Y in the horizontal plane, and this is my del theta. So this is my active, this is my reactive. Reactive means something is coming out in this way, and if something is coming out this way and I am having a screw, I will be having that there will be a counterclockwise couple. So I am having a counterclockwise couple about the Y axis. This will try to lift the nose, and the magnitude I can calculate if I know the mass value and radius of gyration. My I will be 450 into 0.32 square, because the radius of rotation is radius of gyration is given 320 mm. The precision I can calculate because I know that the plane is moving in the space and it is giving a turn. So the tangential velocity is 240 kilometer per hour, and the radius of turning is 60 meter. So using these two values I can calculate the angular velocity of the precision, which is basically giving about the vertical axis to rotate my plane. I am giving this omega precision, which is nothing but the 1.11, and my rotation is 2000 rpm, so I can calculate this rotational angular velocity, and when I will put all the value, I will be able to see the gyroscopic couple, that will be 10.75 kilonewton. Thank you.